good capacitor. But there's also a couple of bumps that you might see in this process. You see those ridges or those shoulders in this curve, and those are indicative of some kind of Faradaic process, some sort of reaction. It's typically a very fast reaction, but if it's not fast, you'll know it by changing your sweep rate, and the nature of that shoulder will change significantly because the reaction won't be able to keep up with the sweep rate. Okay? When we go to measure capacitance, as I said, it's the change, it's a charge accumulation as a function of a voltage change. The scan rate here typically is done between 2 and 100 millivolts per second, although lately people have been going to even higher rates. If you want to look at this from a integration standpoint, then what you would do is you would just say, well, this current or this capacitance is going to be half of the area under that curve, under that current voltage curve, which you could have a computer calculate that for you, divided by this voltage difference. Okay, so that's a pretty simple way to think about this. The other type of test that's typically done is a charge-discharge process. So instead of doing a voltage sweep, what you would do is you would charge your device at a constant current, and then you would immediately switch the direction of the current and discharge your device. And what you would be measuring in this case is the voltage. Okay, so you have a voltage that you're measuring. So the current is in the red here, voltage is in the blue. And what we usually watch for, first of all, is you'd see again this, if the current is constant, then you would take the slope of your voltage as a function of time, and that would give you your effective sweep rate. It would be changing potentially during the test, so it would be at a certain point, but you could take some averages that would give you your capacitance. So your current, which is constant in this test, divided by your sweep rate, which is the change in voltage with time which you would measure, that's going to give you a capacitance. However, something interesting happens at the switch point. That's when you switch from positive to negative current, or charging to discharging. And you'll see that there's a drop in the voltage at that point. That actually is a very useful thing to measure because it tells you how much internal resistance is in your device. Okay? So if you can measure that quick drop, that voltage drop here, that can be used to tell you what your internal resistance is. Okay? And the factor of 2 that's in that equation comes from the fact that your current has actually switched double. Right? I was using a positive current, let's say it's 1 amp, and then I immediately switched to minus 1 amp. Well, that's actually a difference of 2 amps. Okay? So looking at this, some general characteristics, I want to give you an idea for numbers. Okay, so how much should you expect? Once you conduct these measurements, how much capacitance should you expect to have? And normally, as I've said before, we normalize by mass or volume. So we make a specific capacitance measurement, or we actually measure, of course, pure capacitance, and then we divide by the mass of our materials. Here are some different carbons that are shown here, and then at the bottom we have some ruthenium oxides. I told you yesterday that those are very good pseudocapacitive materials, and then at the bottom here we have a conducting polymer. But you look at most of these tests were done with KOH, either in organic, some aqueous, the sulfuric acid would be in aqueous solution. But the capacitance per gram is an important factor. So kind of the first thing you would do once you've done your test, once you've measured your capacitance, is to normalize by the mass. So if you get 100 farads per gram, you're doing pretty well, although you can really boost that up with pseudocapacitance. That's what the ruthenium oxide does, and you can see that you can get even close to 1,000 farads per gram. And then the capacitance per volume, usually the volume is listed in cubic centimeters, is typically of order 100, although once you start to divide by the active material volume, that can be very small, and dividing by a small number almost always gives you a very large number. So that's why you see some really big numbers for the ruthenium oxide here. Okay, I think that, personally, the volume part of this is just as important as the mass part. I think early in the study of supercapacitors and batteries, people really focused on the mass, but it turns out that the volume is really important too, from an engineering standpoint. Fitting something into a device. I think most of you can appreciate that, right? You would probably, as you think about your cell phone, right, you feel how heavy it is, and you kind of notice that, but what you notice more is how bulky it is, how big it is, and having a little bit of extra weight is not as inconvenient as having a little bit of extra volume. Right, because people are always trying to make these devices fit into smaller and smaller places, and putting them in their pockets and so forth. And having a device that's small in volume, I think, is tends to be more appealing to consumers. All right, I'm going to go through some examples here, and what I want to do with this is to actually show you. I'm going to walk you through how you make making a material, and I've talked a little bit about this before, and this comes from our own work, but then marching through the testing that was done and the results and how we interpreted those results in a real material. So here's a reactor that produces these graphitic petals, which I'll show you in a moment. Here we're talking about a plasma reactor that puts in typically about 500 watts of microwave power. We have hydrogen and methane feeding the process, and that produces those petals. This lecture is not about that, but I want to connect it back to some of the things we talked about before, which is how to make the materials in the first place. So don't think for a moment that making the materials was simple or easy here. It was a significant challenge. And this is what the materials look like. They come out, and you can see that we start out, and these are some different levels of time durations on the left side, on the left panel, showing more and more, longer and longer petals being grown, and then a close-up on the right side. And we have about almost a billion petals per square centimeter, and what that gives us is several hundred square centimeters of surface area, true surface area, for every 1 square centimeter of Euclidean area. Euclidean area is the projected area. It's what you would see if you held it away from you, how much area is there. And so the interesting thing is that we have no metal catalysts were used in the process, so the petals form just by virtue of having the carbon come in and deposit. And I'm not even sure, we heard in the last lecture, Ritu talked about leaves and grass, right? And is this leaves or grass? I mean, it looks like petals. I guess what I should be talking about, it's the growth as opposed to deposition, but this is some kind of combination, because really what happens is the carbon comes down out of the plasma and deposits on the surface and then self-organizes and grows. So this is really kind of both. It comes from the top and then it grows out. So this is what carbon cloth looks like. I mentioned it once before. It's a very useful material in the laboratory because it hangs together. It's already woven so that you don't have to be chasing strands of fiber around all over the place. And so it's woven in this way. This is what it starts looking like in panel A. But in panel B, after we've grown petals on it, you could see that it's decorated. It looks to be, uniformly affecting the fibers all around. So in other words, it penetrates into the cloth itself. And so what we did in this work was to take the petal, and we added a layer of polyaniline. Polyaniline is one of those polymers that has a pseudocapacitance to it. And so in our case, what we did, when we say we functionalized it with polyaniline, we used an electrodeposition process for the polymer itself. Not too difficult to do. You can do it in your lab with just some simple tools. We use polyaniline as opposed to, for example, other pseudocapacitive materials like ruthenium oxide, because it's inexpensive, it's easy to process, okay? It's reasonably electrically conductive, which is a problem for many pseudocapacitive materials. If you put the pseudocapacitive layer on the surface of the carbon and you make it too thick, then you're going to introduce more and more resistance in your device, and you don't want that. It also has multiple oxidation states, and theoretically has very, very high capacitance per unit mass of the polyaniline itself. So that's what we did. And it turns out we were able to find a way to coat that polyaniline conformally. I mentioned that earlier. Being able to coat the material conformally is important. So here's an example of results for these petals with polyaniline. And we're talking here about the CV curve as a function of scan rate. And the first thing you should look for in this curve is, does it look fairly rectangular? I see some shaking heads, no, right? It's not too bad. It's not too bad. But you can see that it's more rectangular if you really look carefully, like as you go to the lower scan rate. So this goes all the way from 2 millivolts per second to 100 millivolts per second. The lower scan rates are more rectangular than the higher ones that are just sort of buried in the middle, because at higher scan rates, if I increase dV dt, then I get higher currents, and so the whole area grows, right? That doesn't mean my capacitance has changed necessarily, right? It's because the capacitance is the ratio of current, which is the vertical axis to scan rate. But then I also see these shoulders. So the shoulders are important to look for, because if you put something like polyaniline into your system, you did that so that you would have some pseudocapacitance. And if you don't see the shoulders, then your pseudocapacitive material is not working. Okay? And so it's important that you actually want to see these shoulders prominently featured, in fact. You can also look at this, once you actually calculate the integrals, to calculate the capacitances. One of the things that you'll look for in a device is whether your scan rate is causing you to lose apparent capacitance, right? So if I go really slow, the lowest scan rates, then I will have a closer to a perfect rectangle with those humps added, okay? Those pseudocapacitive peaks, those redox peaks. And you can see that. If you look at the lower scan rates here in this chart on the right, panel D, you will see that for the low scan rates, I actually have higher apparent capacitance, right? I have, significantly higher. And then as I increase my scan rate, it drops down, because what's happening is there's an internal resistive effect, so that the system, the reactions, are not able to keep up with the scan rate perfectly. And so I start to smooth out those corners of my rectangle, and I have therefore less area inside of my CV curve. Okay? Now, a couple of other things about this, relating it back to the materials. On the right panel, we're showing a few different curves. On the bottom, we have just carbon cloth and polyaniline. Okay, so we have a respectable, but not tremendously good, specific capacitance for that. But then we add the petals, right? And you see that the capacitance jumps by a factor of 2 to 3. So the pedals add 2 to 3 times the capacitance. So that's a surface area effect. Okay? On this dashed curve, I'll talk about it later. The dashed curve here is for BP, which is Bucky paper. I'll tell you what that is later. Graphitic pedals, that's GP. Okay? And an oxide. Instead of having the polyaniline, we had an oxide. And so I just put that in as a reference point for later. All right. We now move on to the second characterization technique that I mentioned. That's in the left panel, A, and we have a series of charge discharge curves. In this case, those are at constant current, right? And what you look for in these is general consistency of your curves, although they don't look the same. You can see this, you know, it's plotted as a function of time. So if I have a lower rate, a lower current, then I'm going to have a longer drawn out test, right? One of the advantages, I mean, just think about this as a practitioner, right? You look at this and really the only curves that you could see here are the 1 amp per gram, 5 amp